All right. It's great to be here again, and it's great to see a full room. Okay, so I'm going to be talking about logical relations, as Benjamin just said. So let me just sort of say a few things about setup and what the lectures are going to cover and things like that. Okay, so. So, as Benjamin said, logical relations are one of the most fundamental proof techniques that in programming languages, and you can use them basically for all sorts of things. And that's really, the amazing thing about them, that there's just a vast number of properties for which they're useful. So, just to give you some examples, one of the earliest uses of logical relations was to prove that all terms in the simply typed lambda calculus, all well-typed terms in the simply typed lambda calculus, terminate. So it's a proof that evaluation will always terminate in that language. They have been used to prove observational equivalence in languages. So why would you want to prove observational equivalence or equivalence of programs? Why would you want to prove that two programs are equivalent? Might that be useful? Reasoning about correctness, right? Like suppose you're doing some compiler transformations, right? And you want to show that the program that you had before you transformed it into something else, hopefully a more optimized version, that the two versions are equivalent, right? That they'll behave the same, they'll always give you the same answers. Some other examples, let's say you have two implementations of the same abstract data type, right? Like let's say you're implementing a stack using a linked list versus using an array or something. And you want to reason about the fact that you actually have two implementations that are equivalent. Maybe you started out with the less efficient one, and later on you wanted to plop in a more efficient one. So these are just examples of where you might use them. So equivalence is a big thing. But you also need them in security. And I'll say a little bit more about this later, and Andrew Myers will show you a use of logical relations in one of his lectures as well. But let me do a little bit more setup. One thing that I want you guys to remember is that logical relations essentially come in two flavors. And this is helpful, like mentally, to categorize them as such. There are logical predicates and logical relations. Basically, these are unary, as indicated by the word predicate, as opposed to relation, and these are binary. Okay, and there'll be a certain pattern that emerges during these lectures, which you'll start to sort of understand that this is how I want to set things up. Okay, so unary logical relations are used. What do you do? Okay, what is a logical relation? Well, logical predicates are unary logical relations. What you do is you basically say that the terms in your language satisfy a certain property, a certain predicate. I'll write P for that, and we basically say that E satisfies P, and we index this with a type. So logical relation or logical predicate says, you set up a definition of when all terms in the language of type tau satisfy this predicate or property of interest P. Okay? Binary logical relations, you have two terms. So here I'll write R for relation as opposed to predicate, but you basically set up some sort of relation R, again, indexed by the type, and you say when expressions E of type tau, sorry, you set up a relation on E and E prime, right? So you have two terms. And you say that the terms E and E prime belong to this relation. So here, let's see. We could start talking about, this will be the general pattern of setting up a logical relation when you want to talk about a term E and E prime of type tau being equivalent to each other. Okay, so equivalence is normally, you're going to be thinking about binary logical relations. Examples of using logical predicates or unary logical relations are things like type safety. I can set up a logical relation to show that some E of type tau is type safe, that it will, that a term of that type, if it type checks, it will not get stuck when you run it. Another example is to prove strong normalization of simply typed lambda calculus. Strong normalization is a way of saying that all terms in the well-typed terms in the simply typed lambda calculus will terminate. Okay? All right, so that's an instance of this. So let's say termination in simply typed lambda calculus, for instance, or type safety. examples of uses of unary logical relations. Here, proving observational equivalence, for instance, in various contexts, and in other instance of that is compiler correctness. And actually, let me say something about compiler correctness. You can actually set up logical relations between two terms that don't both belong to the same language. Okay, so you can have a relation that relates source language terms to target language terms. So, the term E and the term E prime could come from two different languages. And actually, for compiler correctness, that's the kind of logical relation that one would want to set up. Yeah?
It seems like that would involve two separate E and tau, E taking tau.
Between E and tau and the E prime and tau?
Yeah.
Yes, exactly. So if you want to think of this as, you start out with a tau in your source language, and perhaps you do a type preserving translation or something of that sort, then what you'd want to think about is, this is my source term. It has type tau, and my compiler translated it to some E prime of type tau plus or tau hat, whatever, translation of tau. And so you set this up sort of, the type of the source level term sort of takes priority, and it sets, tells you what type the other term will have. Yes. Okay. So I'm not going to be setting up those kinds of logical relations where the terms come from two different languages, but I want to show you a pattern where you start to see that this is completely natural, and so that you know how to do it. Okay. Let's see, what else? The other thing that I mentioned before was secure information flow, and this Andrew Myers will talk about a little bit more. But just to give you a sentence or two on what sort of property we want here, well, I'll do that in a second. So Andrew will talk about security type languages where you can essentially label your variables as low security and high security, and then you have a type system which tells you whether or not some high security data leaks into low security outputs. Okay, that's the thing that you want to prevent, and the type system flags that. But now, if you say that I've set my type system up so that it will catch all leaks of high security data into low security observers or outputs, you need to prove something to say that your type system actually does that, right? So what we prove is a property called non-interference. Andrew will explain the details of that. I'm not going to go into it, but the word that I want to mention here is equivalence. Basically, the theorem, non-interference theorem, what it says is that if you have a program and you run it with the same low security inputs, but different low security, sorry, I said that wrong. Let me start over. If you have a program and you have a program P, and let's say it takes a high security input and a low security input, as long as you run it with, you can run it with a different high security input and the same low security input, and you have to be able to get the same low security outputs. So a low security observer should not be able to distinguish the high stuff that you sent in, should not be able to tell the difference looking at the outputs of the program. So it's a form of equivalence. It's a more sophisticated form of equivalence because you have to take into consideration the level of your observer, which is this L here. Anyway, Andrew will get into all of that. But again, the sense that I'm trying to give you guys is all sorts of forms of equivalence, that you want to prove, and you'll find this in many, many different settings. And in my last lecture, I'll give you more examples just to give you a feel for the wide variety of places where these logical relations can be used. Okay, so let me give you a bit more detail on my plan. So today I'm going to talk about strong normalization of simply typed lambda calculus. The fact that all well-typed terms in the language, when you evaluate them, they will terminate. Evaluation will terminate. Okay? Strong normalization for simply typed lambda calculus. All right. I'm starting with this because this is basically the first logical relations proof that most people will encounter, and I want you guys to have encountered it if you haven't seen it already. And what I'm going to do is I'm going to stick to a very standard presentation. Basically the presentation that you will find, give or take, just with a tiny tweak or two, that you will find in Benjamin's TAPL, Types in Programming Languages, Chapter 12. Have that memorized. Okay, but starting tomorrow, I'm going to switch notation on you a little bit. All right, and I'm doing this very, very intentionally because I want you to be completely comfortable with understanding the setup of logical relations and being able to, you know, sort of read papers with one notation or the other and just get the essence out of it. Let's see if we manage to achieve that. But all right, so tomorrow we're going to do type safety using logical relations. And again, this is going to be a unary logical relation, right? Because termination, proving strong normalization, that's a property, it's a unary property. And type safety, again, that a term that type checks will not get stuck. That's also a unary logical relation. And what I'll do is I'll start off doing, you know, showing this for the simply typed lambda calculus, and then I'll add recursive types. Okay? And that'll lead us to some very interesting territory. Basically, logical relations, historically. I said that, you know, you set these up so that you say if E has type tau, you set it up in a way that, you know, for every type tau, you want to show that you want, you basically classify which terms of type, when terms of type tau have the property P. Okay? So this is set up by induction on types. The whole definition is done by structural induction on the type tau. Okay. This works fine, and historically it was great, but it was always restricted to sort of very simple settings where you didn't run into problems and various circularities that come up, like, let's say, when you have recursive types. Because what happens when you have recursive types? When you have recursive types, you can define things like lists and trees and so on. And there are interesting problems that come up with, you know, making sure that this definition remains well-founded. So we'll talk about that tomorrow. So this will be my way to get into how do you have to set up logical relations when you have these more advanced type features. And we'll start with recursive types, and I'll show you step index logical relations. All right? Step indexing has been used. Step indexed. Step indexing is a form of logical relations that's been used with a lot of success in many, many different settings. Basically, anytime you run into certain forms of circularities, this comes in handy. Okay, so we'll talk about that, and then I'll start talking about observational equivalence, how you use logical relations to prove observational equivalence. And here we'll talk about, you know, are people familiar with parametricity, representation independence, at least the terms? Yeah, I see some nods. Okay, good. So we'll talk about those notions here. So we'll start talking about abstract data types and so on. And then, finally, we'll talk about mutable references. Mutable references, as in when you have references in your language, you have dynamic allocation, you can allocate memory on, and you can update it. And these here we'll talk about ML-style sort of references where, you know, a memory cell always contains a value of the same type throughout its lifetime. All right? And this leads to some really, really complicated issues. But we'll see that the step indexing trick just sort of, you know, manages to fix all the problems that come up, in a sense. And that'll be where we stop. But I think that by the time we get over here, you'll have a very good sense of the setup, and you'll be prepared to, you know, read all sorts of latest research papers and so on, even if they're much, much more complicated than what we've covered here. All right? Okay, so let's get into it. Any questions? All right. So let me pull this down. Actually, let me pull the other one down. So here's the simply typed lambda calculus. All right? Hopefully you're all completely familiar with this. But let me just kind of go through it. Okay, so simply type dynamic calculus with booleans added. Okay, so we have booleans and we have functions, right? Tau 1 or tau 2. Expressions in the language include true, false, if then else, and of course variables, abstraction, application, right? Okay, this we're going to look at a call by value lambda calculus. All right. So here are my value forms: true, false, and lambdas. And I've basically defined the operational semantics by giving, you know, the usual Felizen style evaluation context. All right. So this is called by value. So in particular, notice here that when you have application, you evaluate here first, and when that's gotten down to a value, then you evaluate in the argument position, and so on. All right. And here are my reduction rules. So if true, that steps to E1. If false, then that steps to E2. The application case, app case, you have a lambda, it's a value, steps to E with B for X, right? Okay, just getting you familiar with my style of writing things in case it's different from anything, you know, from what's been going on before. All right, and then we have evaluation context here to essentially give you, to define the evaluation order. So we need this rule in order to lift the reduction rules up to the level of full expression. So if you have an expression E that steps to E prime, then we can lift it up to evaluation context using this, right? Okay. Let's look at typing rules. All right, so the form of the typing judgments is going to be that E has type tau under environment gamma. Gamma is a mapping from variables to types, tau. Let me mention a convention. I'm always going to sort of, whenever I write gamma comma X colon tau, I'm going to interpret the gamma to mean disjointness. Okay? So whenever I write something like this, that means that X does not occur in the domain of gamma. All right? Just makes things easier. Okay. So true and false have type bool, if then else, the usual rule. Variables, you have to make sure that X is mapped by gamma to tau, the usual function and application rule. Right? Okay. So what do we want to do? We want to prove strong normalization. What is strong normalization? It is a property that if some expression E has type tau, using these, you know, type checks, using these typing rules, and let me put an empty context here, then E terminates. I'll use this notation. Let me define abbreviations here. So this means that E evaluates all the way to a value V. And basically, it's just sort of another way of writing that E takes a whole bunch of steps and gets to value V, right? Okay. And if I write this and omit the V, then basically what I mean is, sorry, not for all. It means that there exists a value V such that E evaluates to V. All right? Okay. So here's the theorem that we want. Now, I'll let you stare at it for a second. Yeah?
It seems like instead of strong normalization, because you are saying there exists a pathway value instead of that all paths.
No, weak normalization is when all paths to normal forms, all paths reach the same normal form. So if an E evaluates to V1 and E evaluates to V2, then V1 and V2 are the same normal form. Strong normalization is where you say that it must terminate. So this says that if E has type tau, then there exists a value V such that each E reaches V. So evaluating E will always reach a value.
Okay, but in this case, it's even risk anyway. But my point is that strong normalization is typically that each reduction path you can possibly take terminates, right?
No. Oh, yeah, sorry. Yes, that each reduction path you can possibly take terminates, yes.
However, here you only have one, so it doesn't matter.
Yes, exactly. Deterministic. Yes, I was going to make that one.
Okay.
Okay, so evaluation here is deterministic, right? The evaluation order is deterministic. There's no non-determinism in this language. So what does that mean? In particular, that means that, well, yeah, so this is something we rely on in the proof a bit. So in particular, a consequence of that is that if E diverges, then it, you know, it can't be the case that sorry, if E converges, then it can't be the case that it also diverges, right? You could easily reason through that. Fair enough? Okay. All right. Okay. So if I were to ask you to just go off and prove strong normalization, there's the statement of the theorem right there. E is well typed. E has type tau, then E terminates. You want to take a stab at it? How would you prove that? Induct on the derivation. All right. Okay. And induct on the derivation. So, okay. So anyone want to sort of think this through, what might happen? So if we induct on the derivation, let's see. We have the true case and the false case. Clearly, those terminate, right? If then else, all right, so we'll apply our induction hypothesis. We know that E terminates, okay, gives us back a Boolean, and we know that E1 and E2 terminate, so, okay, the if then else case should go fine as well, right? Maybe, for those who are kind of following this rough thing. Okay, what about the, okay, let's do the lambda case. Does lambda terminate? Yes, it's already a value, great. How about the application case? If we were just inducting on the derivation, so what do we get from our induction hypothesis? So we're trying to prove that E1 applied to E2. So we know that E1, E2 has type tau. And, you know, the typing rule tells us that E1 has type tau2 arrow tau, E2 has type tau2. Okay, we're trying to show that E1 and E2 terminates. By the induction hypothesis, we know that E1 terminates and that E2 terminates. Now what? What? You would switch to a different proof method, exactly, right? Okay, so what just happened? Well, if E1 terminates, then it has to, it's a function type, all right? So it has to be a lambda of some form. E2 terminates, let's just call it, it evaluates to some sort of V2. So now we still have to show that E1 applied to E2 terminates. That means what's happened so far, we've taken a bunch of steps. E1 has become turned into this, you know, has evaluated to this lambda. Lambda has gotten applied to a V2. So after a bunch of steps, we're here. But now we have to show that E with V2 for X terminates. Still have to show that, right? And now there's nothing more that our induction hypothesis gives us. We were doing induction on the typing derivation. Or you can think of it as induction on the structure of E, on the size of E. These are all sort of equivalent ways of saying the same thing. But basically, our induction hypothesis here isn't strong enough. All right? And that's where logical relations come in. At its core, logical relations are a way of strengthening your induction hypothesis enough to get a lot of these properties of interest through. And the problem case will almost always be, you know, something to do with the lambda form, with functions. Not always. There are more advanced features that complicate life too, but at least for starters. Okay, all right, so okay, just wanted to make sure I hadn't missed anything. All right, so what we're going to do is define a predicate, a logical predicate or a unary logical relation. So I'm going to call it Sn tau. Okay? So the way to read this is some expression E of type tau belongs to this set that I'm going to define called Sn for strongly normalizing. Okay? All right. We're going to do this by induction on the structure of the type tau. All right, so what are our cases going to be? Actually, let me just read. What types do we have to consider? Up there, my types are Booleans and tau 1 or tau 2. So I'm going to have two cases. All right, so for Booleans, we want to say that E, an expression E of type bool, is strongly normalizing. So what we want to do, and what you generally want to do for most logical relations, is you want to set up this relation or this predicate so that it satisfies three different conditions. All right? The first thing that you want to say is that you want to say that E has this type. So in general, let's just talk about this for some arbitrary predicate P. So usually we define something like this. We want, in the definition, we want to make sure that three conditions are satisfied. The first one is we want to say that E should have type tau. Okay? We want to build this condition in. You can also set up untyped logical relations, slightly separate topic. We'll talk about that later. Okay. The second thing you want to do is you want to say, you want to define this predicate so that so that it requires that E has the property of interest. Okay? In this case, the property of interest is that evaluation of E must terminate. That's the condition we're interested in. Okay, so let's just keep that in mind, and we'll go back and build the definition in a second. And then there's a third condition. So this condition basically says, this is the part where you need to, what we just saw in our attempted proof of strong normalization was that we didn't have a strong enough induction hypothesis. All right? And why wasn't it strong enough? In a nutshell, it wasn't strong enough because it didn't capture something about what happened at the elim form for functions. The elimination form for functions is application, right? Someone gives you a function. What do you do with it? You apply it. Okay? But when you apply it, something happened, right? We had a lambda term. It was being applied to a V2. And then we needed to know something about the body of the lambda after the beta reduction, right? We needed to know something about how that behaved. So backing up for a second, this condition that we want needs to say that membership in the relation is preserved by evaluation of elim forms. It's preserved by the elim forms, okay? And we'll see that this is not always sort of built in, but okay, I'll get to that in a second. Logical relation is preserved by evaluation of elim forms. Okay? And for us, what that's going to mean for this particular thing is that when you, let's say in the case of lambda, when you do an application, you want the expression to still belong to the logical relation. So let's get to that concretely. All right, so we want to build this. I have an expression. I want to say that this expression at type bool is strongly normalizing. So let's build it with all of these conditions. So we're going to say that E must have type bool. So E is strongly normalizing at type bool. If E has type bool, that's condition one. If the E has the property of interest, so we want it to be the case that evaluation of E terminates. And by the way, here E is a closed expression, so keep that in mind for now. The relation that we're building is a relation on closed terms. It doesn't have any free variables. Okay, we'll generalize it to free variables later. All right, so that's condition two. Condition three, the logical relation is preserved by the evaluation of elim forms. What's the elim form for bool? If, okay. But I'm not going to build anything more into this. And I'll come back to that in a second. When we did our naive proof earlier for using just induction on the structure of the derivation, if went through just fine, right? Nothing went wrong there. Keep that in mind for a second. Okay, so we're done with bool. Now let's talk about functions. When is an expression of type tau 1 or tau 2 strongly normalizing? Well, it better have the type tau 1 or tau 2. It's an expression. It's not a lambda yet. It better terminate. And this is where we need a third condition about the elim forms. What we want here is, basically we want to say that given an arbitrary, let's call it E1, such that E1 is a strongly normalizing expression of the argument type, it better be the case that when we take E, our expression of function type, and apply it to this E1, we get a strongly normalizing expression at the result type, tau2. Now we'll see this in a proof for a second, but basically what we're trying to build in is this third condition. If you give me an input, an argument that is strongly normalizing, then applying the function, essentially, to that argument will be strongly normalizing as well. So this, we're building in this requirement into the definition. Okay. Now, is this definition well-founded? We were defining it by induction on the structure of the type, right? So here, this looks perfectly well-founded. Here, when we define it for tau1 or tau2, we're defining the set Sn, essentially, right? The set of expressions Sn at the type tau1 or tau2, but in the definition, we only use Sn, the definition of Sn at a smaller type, tau1, and a smaller type, tau2. So yes, this is well-founded, because these types are smaller than tau1 or tau2, right? Okay. All right, so now let's see. So one thing that I want to, let's mention that. I'm just going to erase this. Is that all right with everyone? Okay. Okay, so notice, we've just built this relation. Now, the theorem that we want to prove is still the one up there, right? That if E is well-typed, then it terminates. Evaluation terminates. Okay. So how does this definition of Sn fit in? Basically, what we're going to do is we're going to do the proof in two parts. We're going to show that if E has type tau, a closed term, then it is strongly normalizing, or it belongs to the set that we've just built. All right, so this is going to be part one of our proof, or one lemma. And the other lemma that we're going to prove then is that any term E of type tau that is strongly normalizing, or rather, whenever E belongs to this set Sn, then if you evaluate it, it will terminate. Yeah.
Yeah, because it's a condition.
Precisely. I just want to make it completely obvious, right? So what he just said is that proving 2 is a no-brainer, essentially, right? Because we've built it into the definition. I mean, look at it. How would we, let's prove 2, just to convince ourselves completely, all right? So how would we prove 2? Well, let's prove it by induction on tau, all right? We have two cases. We have a case for Booleans. We have to show that E terminates. Oh, the definition tells us that it does. So we're good, right? There it is. Okay. Now we have to consider the case where tau is a function type, tau1 or tau2, right? We have to show that the expression terminates. Okay, let's go look at the definition. Oh, right here. Okay, so basically, this is trivial. We've built our definition so that the property of interest is built in by definition. So really, all the work is in this first lemma right here. We have to show that every well-typed term, every well-typed closed term at least, of type tau belongs to the set Sn at type tau. Okay? So let's take a look at how we would do that. Yeah?
What part of what you're doing is in the semantical part, and what part is it in the proof? Because you defined this Sn and you said, well, this is the condition.
Yeah.
Are those semantical conditions? Or what is
Semantic how? In what sense are you using?
I mean, you wanted to mean something, but then you said, well,
Okay, so, well, let me try to get us out of that. Okay, so what I'm building, if you think about it in a semantic sense, right? I'm building a set or a model, right? I'm calling it the set Sn. And I want that set to be inhabited by all terms that terminate, right? Essentially, that's the semantics for now, you know, of what the set Sn is. Okay, but basically, all Sn is just sort of a way of strengthening our induction hypothesis so that we can prove that any well-typed term does, in fact, belong to the set Sn at the appropriate type. Does that make sense? Every well-typed term must belong to this set or this model, you know, that we built. Okay? Yeah.
So can I understand? Here is to define some logical relations which is as strong as the one that we want to prove, then prove that one instead.
If you want to define, say that again.
So here is to define some logical relations which is as strong as the one we want to prove, which is determinate, then prove that one instead.
Yes, exactly. I mean, and you need to go through this condition because it allows you induction hypothesis. Okay? Because when we tried to prove this directly, going from here to here, we failed because our induction hypothesis wasn't strong enough. Okay? And this will become a little more clear as we step through the function case and of the proofs. Okay. But we still have another problem. Okay. We have defined when closed terms are strongly normalizing, right? And the theorem that we're interested in is about closed terms. If you have E, it's a closed term of type tau. It doesn't have any free variables, right? It type checks under the empty environment. Then we want to show that it terminates. Now, here's the thing that we're trying to prove. How would we prove this? Again, just the mechanics of how would you, here's a theorem or a lemma, how would you prove this? By induction on? By induction on the derivation, okay? I think that's exactly, completely the most logical thing to do. So if we do induction on this derivation, we are going to hit the lambda case, right? At that point, even though we're trying to prove this for a closed term, in our premise, we're going to have some free variables, right? So we can't just prove this for closed terms. We have to generalize. We can't prove this directly. We have to prove some theorem about open terms. So if E has type tau, it's well typed under gamma, then what? Well, then we basically want to say that we want a certain way of closing off all of the free variables that appear in E with appropriate values. So let's do that with a substitution. I'm going to write little gamma to be in a substitution, and basically it means that it's a mapping from term variables to values. Yeah.
Can you just say the S for all at the beginning, and if the S for all is at the beginning, then this expression term like it's probably not normalizing or whatever, the one which doesn't act for all.
So tell me about for all. Would you ask?
Just for all the free variables.
For all the free variables? Okay, so that's sort of what we're trying to do. We're trying to say that for all the free variables that appear in gamma, if you give me values that have a certain property to substitute for these free variables, and that's what these values are. I'm just trying to write in the sort of substitution for shorthand. You give me some, for all values, v1 through vn, you give it to me. I want to be able to plug those in, essentially, right? So what I want to do is, since E is an open term, I want a closed term. So I want to close it off with a substitution and then prove that that is strongly normalizing. Of course, there's a question mark here. Are you with me? So we have a property, strong normalization, which applies only to closed terms. We're trying to sort of lift that notion up to what do we need to do for open terms? Because we need to talk about open terms in order to, you know, actually get the proof to go through. Yeah.
For
Oh, you meant lambdas. Oh, just to close them off? Oh, I see. So if you just have E, that doesn't quite work. Try it out. I mean, yeah. To get it to work, you'll essentially have to do something like what we're doing. Because at some point, you basically have to hit the lambda case. And that will add variables to your environment. Right? Okay. All right. So what I'm trying to say here is that I have a term with some free variables, and I'm asking you to give me a substitution gamma, which gives me bindings for all of the free variables in gamma. And then I want to use that substitution to close off my term and then prove that the closed term belongs to this set Sn that I've defined. Okay? So what conditions do we want on gamma? We want this substitution, this arbitrary substitution that we're being given, to satisfy our environment in some way. Okay? Haven't defined that yet, but we want it to satisfy our environment gamma in some way. Okay, so what does that mean? Basically what we want is, we'll say that little gamma, the substitution, satisfies big gamma, type environment, if they have the same domain. So the domain of little gamma is equal to the domain of big gamma, so basically, they're mapping the same variables. And if for all variables in the domain of either gamma, is this in front of anyone? Can everyone see this? Okay. For all variables in the domain, we want it to be the case that when we look up the value gamma x, we want that to be strongly normalizing at the appropriate type. Okay? So what we're trying to say is you are giving us a bunch of values, v1 through vn, right? Map x1 map to v1 through xn map to vn. But essentially the point is that this substitution is, in the statement of this theorem, is just a way of you giving me some values, right? Some set of values that I can substitute for my free variables. I need these values to have a certain property. I need them to be strongly normalizing in order to push my proof through. Sort of. I need them to be well behaved in certain ways so that then I can show that when I plug these well behaved values, in this case the well behavedness is that these values are also strongly normalizing. What does it mean for values to be strongly normalizing? Let's pause there for a second. Why am I insisting on these values v1 through vn being strongly normalizing their values? Yes?
I guess the interesting case is when you have a lambda. And you need to show that it accepts a strongly normalizing value as an argument, then it's also fine.
Right. So the interesting bit is not that this value itself. It's already a value. It's already terminated. The interesting case is the bit about the induction hypothesis that we get, right? If that value is of function type, meaning it's a lambda, then we want to know that it belongs to the set Sn tau 1 arrow tau 2 so that we can get this condition, right? This was the bit where we were trying to strengthen our induction hypothesis, and we'll see how this plays into it. All right? So, but the general picture here of this setup, so this is the theorem that we will actually prove, because we can't prove this more restricted form, right, for closed terms. So let me just sort of say another thing about logical relations. Often when it comes to functions, you will hear the slogan that logical relations take related inputs to related outputs. You can use the word related, or you can use the word well-behaved, well-formed, having the property of interest. If you give me things that have the property of interest, the logical relation will give you outputs that have the property of interest. That's what this whole proof device is doing. Okay? And that's what, so I want you to start seeing theorems of this form as that statement. They will always be sort of, something is well typed, has a bunch of free variables. You give me some inputs that have the property of interest. And this is just shorthand for defining that, right? This whole thing was just sort of saying, oh, all the values that you give me that belong to Sn have that property of interest. Then, if I substitute these values that you gave me that are good, right, that have the property of interest into my expression, then I will get a whole expression, a closed expression, that has the property of interest. Okay? Yeah.
Why don't we need an analogical relation? Because in this theorem it's just type of tau. Why don't we need it to be a strongly normalizing?
The E itself?
Yes, that line right there. Why is that not strongly normalizing?
That's what we're trying to prove. If we're trying to
Oh, right, yes, yeah.
So when we close it off, it's strongly normalized. I don't know if I should do this, but I'll do it tomorrow. I'll show you another way of writing this. That sort of makes it more clear, makes the connection to what you just said kind of more clear. But okay. Okay. So what do we need to do next? Here's what we need to do. So this is the theorem that we want to prove. Do I want to do some? Let me just point out one property that we're going to need. Let's just call this a substitution lemma. So we're going to need to show that if you have some E of type tau, right, and you are given some substitution that satisfies gamma in that way. Now notice that all of the values in our substitution, since they belong to this set, they are going to have the type dictated by big gamma, right? So all of these values that are in this substitution will have this type, right? Okay. I could write that as, if you guys have seen that. So for every value in the range of this, for all x in domain of gamma, assuming that the domains of these is the same, it must be the case that gamma x has type dictated by gamma. And these are closed values. Okay? All right, so substitution lemma that I'm interested in, I want to say that if I have a term and I'm given a substitution gamma that satisfies that, then it will always be the case that the closed term that I get by applying my substitution to E is going to have the type tau. This is just a generalization of the standard substitution lemma. We would prove this by induction on the length of big gamma, all right, and sort of or on the size of gamma of the domain of gamma. And the case where n is 1 is your exact substitution lemma that you would see for the simply typed lambda calculus. Yes.
Yeah. Back to the thing before.
Yeah.
Are we considering closed terms being open terms as well?
Sorry.
Is a closed term also an open term with no free variables? So I guess what I'm wondering is you have this point 1, which was one step before that.
Yes.
That's for closed terms, correct?
That's for closed terms.
And so on the right, so I'm wondering if E has no free variables, then we're using the closed term. Okay.
What you're trying to say is that once we prove this theorem that we actually want to follow the corollary.
So where I'm cut up is if E has no free variables,
yes,
then how can we directly just say that E has type tau implies that E is strongly normalized?
E has no free variables. The thing is, you need to prove the more general theorem, right? And then, okay, so let's forget about how we prove this, but let's see how we prove this.
Okay.
Now, let's talk about whether this follows.
Okay.
Does this follow the corollary of values?
Yes, absolutely.
That's the deal.
Okay. So we'll get to that.
We can't prove the corollary directly.
So we're getting to why this is true later?
Yes,
okay.
We're getting to why this is true now.
Okay, my next question is why does this substitution not follow directly from this theorem?
It pretty much does.
Okay.
I just wanted to state it.
Fabulous. Thank you.
Well, I mean, it doesn't follow directly from this theorem. We need it in order to prove this theorem at certain points.
Okay, great.
That's just an auxiliary lemma that I wanted to say. Okay.
It would follow if the theorem were already proved.
If the theorem were already proved, it would follow. Yes, exactly. Okay. All right. Okay, so let's prove this theorem. We're going to prove it by induction on the derivation, exactly. So we're going to prove it by induction on this derivation. Let's do a really, really trivial baby case first. Let's do case where E is just true. Okay? All right, what do we have to show? Okay, we say, suppose that we're given an arbitrary, so suppose we're given a gamma that satisfies big gamma in this way. We have to show that gamma applied to true is strongly normalizing at our type bool. Right? This is what we have to prove, and that amounts to this for the case that we're considering. Right? Okay. Now, so we want to show that gamma applied to true belongs to the set Sn at type bool. All right. First, let's note that this is equivalent to showing that true belongs to Sn at bool. Yeah? Because true doesn't have any free variables. Just by definition of substitution, because true doesn't have any free variables, those two things are equivalent. So suffices to show this. Put an L there. Okay, so now we just want to show that true belongs to this set. Let's go and read our definition and see what we need to do to prove that. We need to show that true has type bool, that it's a closed expression of type bool. Good, we're done. We need to show that true terminates. It's already a value, so we're done. Right? Okay, good. So true is really easy. All right. Now let's do something more interesting. Well, let's do the variable case as well. So the case where x has some type tau. Okay. What do we need to do here? Well, again, suppose that we are given a substitution gamma that satisfies our big gamma. We have to show that when we apply the substitution to our expression, which is x, that is strongly normalizing at this type tau, where, this tau is gamma x, right? That's what you can read off here. Okay. So let's try and show that. Well, so this is an arbitrary tau, right? But we know that our substitution gamma satisfies big gamma. So let's go look at the definition of that. So what can we infer from this fact right here, right? That the substitution satisfies big gamma. Well, we know that the domains of the two gammas are the same. So that means that we already know that x is in the domain of big gamma. So that way we know that x is in the domain of little gamma. And we know that gamma x is some value, right, because it's a substitution. And we know that for all x, that value satisfies the property that we want. So this follows immediately. Right? I could just write this as, this is what we need to show. We already have it built in by definition. So this is immediate. Everyone with me? Yeah? Okay, good. All right. Now, how much time do I have? I have till noon, right? Okay, yes. Okay, so now let's do the application case. It turns out that even the application case is now going to be easy. Things are going to be flipped around a little bit. Before, when we were naively trying to do the proof, the application case is where we got stuck. And the lambda case was just fine. Now it's going to be the reverse. And there's a reason for that. Well, we'll get to it in a second. All right, so let's look at the application case. Okay, there's what we want to, there's the case we're considering. So what do we have to do again? So again, we say, so we know that E1 applied to E2 has type tau. We say, suppose that we're given an arbitrary substitution gamma that satisfies our big gamma. We have to show that the closed expression is in our set Sn. So specifically what we have to show is that when we apply gamma to the expression E1, E2, we get an expression that belongs to Sn at what type? At this type tau. Okay? All right. So first, again, let's make an observation about substitution. Notice that just by property of substitution, this expression is equivalent to gamma E1 applied to gamma E2, right? So it suffices to show gamma E1 applied to gamma E2 is strongly normalizing. We're just pushing the substitutions in, right? Okay. Now what? How do we prove this property? By assumption. Okay, so first what you're saying is, let's appeal to the induction hypothesis, right? So we need to appeal to the induction hypothesis. By that, we will know, we know that E1 has type tau 2 arrow tau, right? Okay, so what is the induction hypothesis going to tell us? It's going to tell us that, you know, basically this property holds. By the induction hypothesis, if we can supply a gamma that satisfies this big gamma, right, and we have one here, right, then we can conclude that gamma applied to E1 belongs to the set Sn at the type tau 2 arrow tau. Right? We can infer that just using our induction hypothesis. Okay. Then we can do that one more time, right? Okay, so by IH again, we have that gamma applied to E2 belongs to the set Sn at the type tau 2. Okay. Now, this is the thing that we still want to show. But we're making progress. Starting to look more and more like that, right? Okay. All right. So now, since we know that here's an expression that belongs to Sn at the type tau 2 arrow tau, let's go look at the definition. This is what you were suggesting, right? This definition says that the expression is well typed and that it terminates, but this is the bit that we're interested in. It says that given an arbitrary E1 of the argument type, right, an arbitrary E1 that belongs to Sn tau 1, this property must hold. So we have this expression that we can use as the argument, right? And it belongs to Sn at the argument type tau 2. Therefore, just by unrolling the definition over here, we get that at the result type, which in this case is tau, our gamma E1 applied to this expression gamma E2 must belong to Sn at the type tau. So we got it simply from the definition. Right? Okay, so what did we do? We went and strengthened our induction hypothesis. And we built the case that we were having trouble with, we sort of built a condition about ill-informed into the definition of this relation, which gave us a stronger induction hypothesis that just allowed us to push the application case through really, really simply. All right? But there are always two sides to the coin, all right? Application became really easy because we strengthened our induction hypothesis. Now, the lambda case is going to become harder because we're going to have to prove an extra property about functions. You know, functions can't belong to the set Sn tau 1 or tau 2 simply if they're well typed and if they terminate, which they easily do. But we also have to show that any function that belongs to this has this property that if you give it, if you apply it to an expression that is strongly normalizing, then the application is strongly normalizing. Okay, so let's do that next. Can I erase this? Or should I move? All right. Okay, so lambda x colon tau 1 dot e has type tau 1 arrow tau 2. So that's the case we want to show next. All right. Before I dive into this case, I want to do an auxiliary lemma, okay, which is going to be useful just in terms of making our proof shorter. So you will often use something of this flavor in your proofs whenever you use logical relations. So here's what it is. We want to show that membership in the logical relation is preserved under forward and backward reduction. Okay? What does that mean? Basically that if you have some expression E of type tau, and E takes a step to E prime, a single reduction step to E prime, then we want to show that the following two things are true. A, that if, hold on, I want to do this in a certain order. What did I do here? Okay, yeah. That if E prime is strongly normalizing at type tau, then that implies that E is strongly normalizing at type tau. So in other words, you could think of this as membership in the logical relation is preserved under backward reduction. And then we want the forward reduction case. So if E belongs to Sn tau, then E prime does. Okay? So any guesses as to how we would prove this? We'd prove it by induction on, what would we prove it by induction on? This is going to be your homework for tonight, so. Sorry? The step relation? No. Basically, what you're trying to show is that if this holds, then this holds. So don't dwell on the top. This is the important bit here. Type, exactly. So this is going to be a proof by induction on the structure of the type tau. Please prove this tonight. It's a simple proof, but it just gets you, into the mechanics of how these things work. All right? Okay. So once we have this, sir, yeah.
Open terms.
Here it's not about it being a bad idea. This is just an auxiliary lemma that I defined, so I kind of have some prior knowledge about what I need in there.
Yeah, so
and I'm going to need it for closed stuff. And besides, I don't see the problem is that for open terms, evaluation isn't really defined. It's only a closed term that can take a step up.
okay.
So, all right. So this is what we need to prove. Now, so we have a well-typed lambda, right? A type tau and our tau 2. And we want to prove that if we're given an arbitrary substitution that satisfies gamma, we want to show that closing that off gives us a strongly normalizing term. Okay, so suppose that little gamma satisfies big gamma. Now what we're required to show is that, that gamma, the substitution, applied to lambda x colon tau 1 dot e, gives us a closed term that is strongly normalizing, that belongs to our set at the type tau 1 over tau 2. Okay. Now, what do you think the first step is, just based on if you were paying attention on what I did in the last two cases? Right. Let's push that substitution in. It's going to make our life easier. All right. So here's where that throwaway comment about I assume that comma in environments means disjointness comes in handy, just to see this, really clearly, right? So we know that X does not appear in big gamma. We know that the domains of these two gammas are the same, so we know that X does not appear in little gamma. So we sort of trivially, very easily know that we can push this substitution in. So because gamma is not going to map X. So we get this. That's what we need to show now. All right? Okay. So any guesses? What do we do now? Well, this is what we need to show, right? We need to show that a lambda term belongs to the set, our strongly normalizing set at the type tau 1 arrow tau 2. So that's what we need to show. Let's go look up what we need to show. All right, let's look at the definition. So in order to show that that term belongs to this set, what do we need to do? We need to show that the term we have has the type tau 1 arrow tau 2. So does this term have type tau 1 arrow tau 2 under an empty environment? Yeah? And that's why I defined the substitution lemma. That's what we need, right? Because we have a gamma, we have a lambda that type checks under this big gamma. We are given a substitution. We've applied the substitution to it, and now we know that the closed term has that type as well. So it's just a simple application of the substitution lemma that I put up there. This is where we use it. Okay? All right. So that's condition 1. We needed to show that this term has the right type. So we're done with the first condition. Okay? What's the second condition we have to show? We have to show that the term that we have in our hand, which is that lambda term, terminates. It's a lambda term. It's already a value. So clearly it terminates. Right? So we have to show that this term, this lambda term, terminates. So we're done. That's easy, right? Okay. So really the guts of the proof is that third condition. First two conditions were easy. So now what we sort of have left to show is that given an arbitrary E1 that is strongly normalizing at type tau 1, we need to show that if we apply our lambda to that E1, we get an expression that is strongly normalizing at type tau 2. That's what this says we have to show. All right? So let's say consider an arbitrary E1. Let me not put the shut there. I'll just say consider E1 such that strongly normalizing E1 at the argument type tau 1. And now what we have to show is that our lambda term, lambda x colon tau 1 dot gamma E, when we apply it to this E1, we get an expression that is strongly normalizing at the result type tau 2. Okay? All right. So now talk on how to proceed. You could use a reduction, okay. And what would you like to do? Or what do you? Reduce, exactly. Okay, so basically we know that when we have a lambda applied to an E1, well, this is call by value, right? So the first thing that's going to happen is that E1 is going to get evaluated, right? Okay, so we know that the E1 belongs to Sn at tau 1. So let's use this. E1 belongs to Sn at tau 1. E1 evaluates in some number of steps to, I'll do that on the side here. So E1 is going to take a bunch of steps and eventually evaluate to some value V1. All right? With every single step, because we have this lemma about strong membership in this set being preserved by forward reduction, we can show that the V1 that we eventually get also belongs to this set. Right? So here we have E1, we run it, we evaluate it, we get a V1, and then we know that V1 is also strongly normalizing and that it belongs to the set Sn at tau 1. Okay, so now that means that we have taken this expression, we've evaluated this to a V1. All right? So that means that this expression has taken a bunch of steps, and now we have lambda x colon tau 1 gamma e applied to V1, right? After a bunch of steps. Okay. So if we originally wanted to show that, if we wanted to show that the original expression belongs to the set Sn, now that the expression has taken a bunch of steps, if we could show that the expression that we have now belongs to that set, then we know that the original one would, right? Sorry, that was rather long-winded. We can use that lemma that we've defined about forward reduction in order to show this. Okay, so basically, it now suffices to show that this expression is strongly normalizing. Fair enough? Okay, so now we're going to show this. Okay, and we can do the same thing again, do a beta reduction, and now we end up with, I'm just going to massage this expression right here, we end up with gamma e with V1 for x. So just show that gamma e with V1 for x is strongly normalizing at type tau 2. If we could show this, then we would again be done using our forward-backward reduction lemma. Okay, so this is what we need to show. All right, now what can we do? What have we still not done? Still haven't used our induction hypothesis, right? So let's do that next. We know that the body of the lambda E has type tau 2 under gamma extended with x. So in order to use our induction hypothesis, what do we need to do? We need to supply some sort of substitution that satisfies this extended environment. So we need some sort of gamma prime that satisfies the extended environment gamma x colon tau 1. If we could come up with such a gamma prime, then by the induction hypothesis, we would be able to conclude that gamma prime applied to E is strongly normalizing at the type tau 2. Okay? Help me come up with my gamma prime then. What gamma prime do we want to use here that satisfies this extended environment? Okay, so little gamma we already knew satisfies big gamma, right? So we want to extend it with some x, right? Mapped to some value. And what do we need? Well, we need it to be the case that whatever value we put over there is strongly normalizing at the type tau 1. So just use this V1 that we have, right? We already know this fact. Okay, so take the extended environment, right? So the environment we had before and add in that V1. And this makes sense, right? Look at how the program is running, right? We have this lambda term. It's getting applied to an argument, but the argument got evaluated first, and we got a value in our hands. And then we know that that value is strongly normalizing. This input that we have is strongly normalizing. So we can use that here. All right, so now, because we know that this substitution, this extended substitution satisfies this extended gamma, we know that E with gamma prime is now x maps to V1, and this whole substitution gets applied to E. We know that E substituted with this stuff is in the set Sn at the type tau 2, right? Okay, let's massage this again, because substitution. What is this expression equivalent to? Could we write it in a different way? Notice that this is just equivalent to take gamma applied to E and then substitute V1 for x. Right? Okay. So we already have this fact. What did we want to show? I think it's kind of warm in here and people are getting sleepy. I'm getting warm. Here's what we wanted to show. Here's what we have. We're done. Yay, and it's lunchtime. All right. Okay. So your task for tonight is to do the proof of this lemma right here. All right. That membership in the logical relation is preserved by forward and backward reduction. And I want you to sit down in a quiet space and prove this lemma for yourself. Just a lambda case is sufficient. All right? But step through the details and see where we went back and forth and where things followed from the definition, the induction hypothesis, etc. All right? Logical relations are basically like this. They're sort of like this puzzle. I mean, you fit them in just the right way. You get the definitions exactly right. And if you have done that, then the proofs just sort of magically unfold and everything works out. But getting the definitions right so that the proofs follow is really the whole art here. All right? And then understanding how those, understanding basically how the definitions lead to the proofs is the thing that I want you guys to understand so that you can set this stuff up for yourself. All right? Okay, tomorrow we'll continue with type safety, and I'm going to throw a very different notation at you. Okay? And I'm going to test how much you understood today, basically, in setting up that definition, because we'll just sort of move some parts around and write it in a different way. And I think that'll be a good exercise to make sure that you really understand it. All right, I'll see you tomorrow.